I know how frustrating it can be when your teacher doesn't do a good job explaining this limit problem. They might give you the right answer, but for all the wrong reasons. The answer to this one is not what you think, so stick around so you understand it better like a ninja. So for this problem, the first approach would be to plug in 0 for x, and already you might be wondering, Dave, 1 over 0 is undefined. Doesn't that mean the limit doesn't exist? Well, that's not always the case because let me give you a counterexample to that. See, if I were to have this function y equals x squared over x, it simplifies to y equals x, except in the original function, we are domain restricted at the origin because you cannot divide by 0. But despite the fact that there's discontinuity there isn't jump discontinuity. And if you were to use a pencil test, you would see that if you approach the origin from either the left or the right, you are converging to a limit value of 0. So that doesn't work. Oh, and by the way, for this function, it's not y equals x, believe it or not. And if you want to see why, check out this other video, but I digress. So moving on, your teacher might have confused you even more after class because you might be thinking for y equals sine of 1 over x, if it's an oscillating function, that must mean it can never have a converging limit value because it's always changing, right? Well, I'm going to choose an easier function to work with, y equals sine of x, because for this one, it's very easy for me to graph it without a calculator. And I want to show you that clearly at the origin, for example, once again, the limit is 0 because using the pencil test, you can approach the same value of 0 from the left or the right. So maybe you're confused even more now and you're just wondering, okay, Dave, I feel like I'm stuck. I tried plotting some values, and as I see here in this table, when I plugged in values that are rapidly approaching 0, I'm getting a value like negative 0.306 approximately for a very small x value of 0.0001. And be very careful here because a lot of students will do this. They'll try 5, 6 values and they'll run away with what they think the answer is. But look at this graph here because you'll notice that if you keep taking terms out, you're going to see more and more that the output function y is going to very rapidly keep flipping back and forth between negative and positive values. So what does that tell us about what the limit of the original problem happens to be? Okay, let's move on because that's really not working with what we're doing above. And this table here is not really a proof. So let's get a little bit more mathematically precise in such a way as the following. I want to take sine of 1 over x and be a little strategic about my choices of the input x here. What I want to do is I want to say, okay, x is going to be a term in some infinite series where every single term in that series here will give me an output of 0. So how do I do that? Well, again, I'm going to go back to this easier expression, y equals sine of x. And when I can get the expression for that as a series, we'll take it back to the original y equals sine of 1 over x function and see what it looks like there. Okay, so by inspection and from the unit circle, if you remember, you know that the output y is going to be 0 anywhere x is 0, 2 pi, 4 pi, 6 pi, negative 2 pi, but I won't deal with the negative values in this video. And similarly, I'm going to choose a different point and I'm going to say, okay, well, I want all the cases where y happens to have an output value of 1. And those happen on odd intervals of pi over 2. Now, why am I doing this? Well, what I can do next is I can take these infinite series and write them as a generalized expression in terms of a variable I'll call n. So in other words, sine of x is always going to be 0 whenever x is of the form 2 pi n, where n is this integer greater than 0. And similarly, the function's output will always be 1 whenever the input is of the form pi over 2 times in parentheses 2n plus 1. So what this means then is because we were working with sine of x, and that's not the problem we started with, we do, however, want to take that over to the original problem we're working with and do it in such a way where we can control the output of sine of 1 over x, just like we did above for sine of x. So for the first series, that generalized 2 pi n term, what I'm going to do is I'm going to take the argument of sine of 1 over x, the inside 1 over x part, and I'm just going to simply assign it to 2 pi n, which means that for the original problem we're dealing with, anytime x is of this form 1 over 2 pi n, because of the double reciprocal, we'll be taking a sine of 2 pi n in the function y equals sine of 1 over x. And I'm just using the subscript n here to make it clear that it's a generalized infinite series. And I'll do the same thing for the other case above where sine of x had an output of 1 and taking the reciprocal of both sides. I'm going to give this series a new name, y with the subscript of n, not to be confused with the function y above. Okay, now what I can do is for the original problem, y equals sine of 1 over x, instead of having to worry about taking x as a limit approaching 0, what I want to think about differently here is I want to take n approaching infinity. Because what we're trying to do is we're trying to make 1 over x be incredibly small. And notice how, for this case where x happens to be of that form x sub n, it doesn't matter how small the 1 over x expression gets. For every term of n here, the output of the function will always be 0. We'll repeat that now by simply plugging in the other series where x is of that form y sub n. And again, no matter how small 1 over x gets, we're always going to have an output of 1. So what does this tell us? Well, mathematically, we're showing that we cannot converge to a specific limit value because already we have these two infinite series that are giving us two different values here. And what does that look like graphically? Well, remember we talked about how you might have thought that because the function oscillates, that it doesn't have a limit, and how I showed you that's not always the case. Well, going back to this table in this particular example, to better understand what's going on visually, if you were to take more terms out here, the reason the limit doesn't exist for this original problem is that more and more as you get really small values of x, you're rapidly oscillating between positive and negative output y values like crazy. Oh, and by the way, speaking of that, so I know this video was about having a misunderstanding of this problem. Here's another video for you for a common misunderstood way of using L'Hopital's